In this lecture, we're going to look at vector projections. So ultimately, we want to say what it means to project one vector onto another vector. But before we look at vectors, let's talk about what it means to project a point onto a line. So first, let's project a point onto a line in R2. Consider the point 3, 2, and suppose I want to project that onto the x-axis. What does it mean to project this point onto the x-axis? Well, what we're looking for is the point on the x-axis which is closest to the point 3, 2. So to find that, we would just drop straight down in a perpendicular fashion and conclude that the projection of this point onto the x-axis is 3, 0. Likewise, if I want to take the point 3, 2 and project it onto the y-axis, then we would just travel straight to the left and say that the projection of 3, 2 onto the y-axis is 0, 2. Computing the projections of this point onto either of the coordinate axes is easy, but we can also project the point onto a line which passes through the origin at an angle. So in particular, consider this line right here. I don't have a formula for it, but just imagine that we have this line. Visually, let's make sense of what it would be to project the point 3, 2 onto this line. The projection of the point 3, 2 onto this line should return us the point on the line which is closest to the point 3, 2. So that would mean traveling at an angle like this so that we follow the shortest route from the point to the line. Therefore, this point right here is the projection of 3, 2 onto this line. We can also project a point onto a plane that passes through the origin in R3. In particular, let's look at the 3 coordinate planes. And suppose I want to project the point P, 3, 4, 5, onto each of the coordinate planes. Well, again, the idea is you want to drop straight down to the plane in question and figure out where this point would land. So if I wanted to drop straight down onto the xy plane, that would mean zeroing out the z component. So the projection of P onto the xy plane would be 3, 4, 0. The projection of P onto the yz plane would return the point on the yz plane closest to this point. So you would want to travel 3 units towards that plane to zero out the x coordinate. So the projection onto the yz plane would be 0, 4, 5. And the projection onto the xz plane on the left would be 3, 0, 5. Now let's get to the topic of interest, which is projecting one vector onto another. So given two vectors A and B, the part of A which lies parallel to B, so which lies in the direction of B, is what we call the projection of A onto B. We denote it like this, so I always think of it as the projection of A onto B. So A is kind of on B. Okay, what do I mean by the part of A which lies in the direction of B? I like to think of it like a shadow. So let's say B is flat ground and the sun is directly overhead. Then the projection of A onto B is the shadow that A cast on B. So in particular, this vector would be the projection of A onto B. So that's the part of A that lies in the direction of B. Okay, for this particular example, our vector A is 5, 3, and B is 2, 0. So how would we project A onto B? Well, we would figure out how much of A lies parallel to the x-axis. And since we map this vector kind of straight down, the projection of A onto B would be 5, 0. Notice here, all I used is that B lies along the x-axis. So B gave me my flat ground to cast my shadow down onto, but I never used the fact that B was the vector 2, 0. So if I took A and I projected it onto twice B, so that I projected it onto the vector 4, 0, A would still cast the same shadow. So the projection of A onto twice B would also be 5, 0. In fact, it doesn't even matter if A and B are pointing in the same direction or if B is pointing in the opposite direction. All B is doing is defining my flat ground where I cast my shadow. So if I took B and I flipped it, so I scalar multiplied it by -1, A would still cast the same shadow onto the x-axis. So the projection of A onto -B would be 5, 0 as well. So what we notice here is that the magnitude of B doesn't matter. Quick example before we go on to a more interesting example with vector projection. What would be the projection of A onto the vector J? So that's the second standard basis vector. That would be like the shadow that A would cast on the y-axis. So now I imagine projecting A onto the y-axis, and that projection would return the vector 0, 3. All the examples we've looked at so far were fairly simple because we were projecting onto coordinate planes or coordinate axes. What happens if we have two vectors like this, where, say, we want to project A onto B, but B is not parallel to I or J? So we're looking at a situation which is more interesting than projecting onto just the x-axis or the y-axis. Okay, we're going to derive the formula, and the formula works in Rn in general. These two vectors look like they're living in R2, but it works in R3 as well. We'll do a basic proof. And if I denote the angle between A and B by theta, the proof we're going to do is for the case where theta is between 0 and pi over 2. If you wanted to look at the case where theta is between pi over 2 and pi, you would just need to make a couple adjustments. Okay, I don't know if you can see it in the picture, but this is the projection that we're looking for. So that's the shadow that A cast onto B. It's a vector which is parallel to B. So it can be written as k times B for some scalar value k. So ultimately what we're going to do is figure out what that scalar needs to look like. Okay, our strategy is going to take this angle theta here and write it two different ways. It's the same angle, so it's going to be the same value of cosine theta. So once we've written it two different ways, we'll just equate them. Okay, so for the first way, notice I've taken this picture and I've completed it into a right triangle by kind of dropping this dotted line straight down to B. Gives us the projection, but it also gives us a right triangle here. And we know that cosine is adjacent over hypotenuse. So cosine of theta is going to be the length of the adjacent side, so that's the length of KB, all over the length of the hypotenuse of that right triangle, but that's the length of A. With our assumption that theta is between 0 and pi over 2, that means that k is greater than 0. So I can simplify this and write k times the length of B divided by the length of A. Okay, that's one way to write cosine theta using SOHCAHTOA. The other way to write cosine theta is going to be using the dot product, so this might be a newer formula. And that is, we have two vectors here, A and B. Theta is the angle between them. So we can say that cosine theta is A dot B divided by the length of A times the length of B. Now we have two equally valid expressions for cosine theta. Let's set them equal to each other. So to start with, we had k times the length of B all over the length of A. And then we found A dot B all over the length of A times the length of B. We can do some simplifications, so let's multiply both sides by the length of A. That cancels that out of the denominator. What we're looking for is that scalar k. So now if I divide both sides by the length of B, we can solve for k. And we find that that scalar k that we're looking for is A dot B all over the length of B squared. Recall that the square of the magnitude of a vector can be rewritten as that vector dotted with itself. So while this is a perfectly fine expression, you could also write a dot b all over b dot b. And that's really up to you which one you prefer. So they're both totally fine. Okay, so now the projection that we're looking for is k times b, where we found k. Notice a dot b is a number, b dot b is a number, so k is indeed a scalar. And we can say that thus, the projection of a onto b is equal to k times b, but that's a dot b divided by b dot b, so that's k, all times the vector b. Or you could write a dot b divided by the length of b squared times b. Both of those are common ways to write the projection of a onto b. I want to mention one other thing here, which is that I could also write this as a dot b all over. Now let me take one copy of the magnitude of b and move it over to the right. So I'm going to divide this by just magnitude of b, and then I'm going to write b divided by its own magnitude. And the reason why I'm doing that is that b divided by its own magnitude is a unit vector. So this says how we would scale a unit vector. The unit vector gives us a sense of direction. This gives us the length. So this is actually the length of the projection, and sometimes that's called the scalar projection. So that's the length of the projection of a onto b. Personally, this is how I usually think of projection, so that's the formula that I usually use. But again, that's just a choice that I make in the denominator, but there's nothing wrong with taking b dot b and replacing it with the magnitude of b squared. Okay, next we'll look at an example. We want to find the projection of a onto b, where a is -3, 3, and b is 2, 1, which is actually pictured to scale here. So this scenario is actually not the case that we proved a second ago where theta was between 0 and pi over 2. Notice here that the angle between a and b is between pi over 2 and pi, but that's okay. It's going to be the same formula. So let me copy the same formula down as before. Okay, so that's the projection of a onto b. So we can say that the projection of this vector a onto b is going to be the dot product of a and b. So let me write -3, 3 dotted with 2, 1, all over 2, 1 dotted with itself, or you could say the length of 2, 1 squared. Okay, that's that scalar k that we solved for, and then we take that scalar and we multiply it by b itself. So all of that times the vector 2, 1. Okay, let's see, what do we get in the numerator? That's going to be -6 plus 3 is -3. In the denominator, we have 4 plus 1, so that's 5. So -3/5 times 2, 1. Or in other words, that red vector pointing southwest is the vector -6/5, -3/5. Okay, let's finish this lecture with a look at orthogonal decomposition of one vector with respect to another. So we are going to orthogonally decompose the vector A with respect to B. So what I call A parallel, so A subscript parallel, is how much of A is parallel to B. So A parallel is this component right here. A perpendicular is how much of A lies perpendicular to B. So this dotted vector here that's kind of going from B up to A, this is A perpendicular. And this decomposition says that if you do the vector sum, so you start at the tail of A parallel, go to the head of A parallel, then put the tail of A perpendicular there and go to the head of A perpendicular, A can be decomposed as A parallel plus A perpendicular. A parallel we recognize as the projection of A onto B. So this is the projection of A onto B that we've been looking at in this lecture. We don't have a great standalone formula for A perpendicular, we just recognize that A perpendicular is A minus A parallel. So that means that A perpendicular is A minus A dot B divided by B dot B times B. We'll see an application of orthogonal decomposition when we look at work. Thank you for your attention.